Good afternoon. On a sunny Monday afternoon. So in the lab this week, you will determining the molarity of a strong acid, and the goal is to determine the concentration of a solution of hydrochloric acid using titration methods. So you need to know about titration, acid-base chemistry, which you don't know much about yet because I haven't been there yet, and stoichiometry, but this is how it is. You can't totally parallelize the lecture with the labs. So you will be graded on precision in this experiment, and I hope you will be also graded on accuracy, not precision, because you can be totally off, very precise and totally off. So if you stand in front of a dartboard, can I have your undivided attention now, please? You will be standing in front of a dartboard and you're throwing darts. And your goal is to get as many darts and right in the bullseye in the center, if this is the game, of course, okay? So you could also hit the wall accidentally. Every time you hit the same spot on the wall, you're extremely precise, but you're not very accurate at all, okay? If the goal is hitting the bullseye. So accuracy alone will not, precision will not, you're extremely precise. Precision will not do it. You need to be accurate also, and this is sort of written in the manual, and I hope you will be also graded on accuracy and not on precision alone. So, because that's not the goal. The goal is to do an analytical technique, and you need to find out what is reality and not what you can reproduce, which is not real, okay? So, the last time we had this beautiful lecture by Greg Dellinger, and we are talking about bonding at the moment, very simple types of bonding, where we use that Lewis-Dot structure to determine the number of bonds and how the bonding occurs to some extent. And it's a simple model, and we're going to expand on this model, and you have expanded a little bit more on this model in the last lecture. You spoke about resonances and bond order. And resonances are identical structure, they have just the bond alternating. So you spoke, for example, about ozone. Ozone, let's see, is 3 times 6 valence electrons. 6 valence electron per oxygen. This is 18, okay? That's an 18 electron system. If you have to divide or distribute 18 electrons between 3 partners, that's the only way to do that, okay? So this will help you with other systems. If you have 3 partners and you have 18 electrons, that's how you do that. So you have 2 resonance structures, and the bond order is now, you have, this would be the central atom, and you have 1, 2, 3 bonds between them, okay, and you have 2 partners. 3 bonds divided by 2 partners is the bond order 1.5, okay? So this will, so it's not a single bond, and the bond order would be 1. It's the bond order would be 2 if it's a double bond. So it's in between. A single bond and a double bond and a triple bond gets shorter as in bond length, okay, because it's stronger. The triple bond is stronger than the double bond, and the double bond is stronger than the single bond. So the longest bond length would be the single bond, double bond, triple bond. So the bond order would be 1.5, so it has a mesomeric structure, it has a resonance, it can be either that or that, but actually it's both, and it's in between. The electronic cloud is oscillating between this, and so the bond order is 1.5. Now we have the carbonate system, CO3, 2-. So we have carbon, how many valence electrons? 4. And then we have 3 oxygens. 3 times 6 is 18, plus 4 is 22 electrons, and then we are 2-. Here's 1-, here's 1-. So 22 plus 2 is 24 electrons. If you have a 24 electron system and you have 3 partners or 4 partners or 3 bonds, one is bound to 3 different things, then you have the only distribution you can do is something like this. And think about it, when you have 4 atoms in a 24 electron system, that's how you do it. So you have 3 resonance structures, and the double bond can be here, here, or here, so actually it's everywhere. The electronic cloud resonates around these 3 oxygens and the carbon. So what is the bond order? You have 1, 2, 3, 4 bonds between 1, 2, 3 partners distributed, 3 what was that? We had how many bonds? 4 divided by 3 is 1 1/3 bond order. So this is a stronger bond than this one, for example. Bond order is only 1.5, but it's not 2, all right? 2 would be even stronger. Now, the last example, we have a C6H6. This is benzene, 1, 2, 3, 4, 5, 6 carbons, and 12 hydrogens, and 6 hydrogens, I'm sorry, C6H6. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds, and 6 bonding partners. 9 divided by 6 is 1.5. With this, you get the bond order 1.5, all right? So which one is the strongest bond? This one here, okay? This is here the carbon is the strongest bond. See that? Bond order is 1.5. Or this is the same than this. So these two are the same, and this is weaker compared to this and that. Let's put it that way. So, and then you talked about formal charges, and I'm going to give you some rules about formal charges. So this, you treat this as if the bonding between the partners would be covalent. Covalent, that means that there's an equal sharing, but there are some rules. So the formal charge is the number of valence electrons at the free atom minus number of valence electrons in the atom inside the molecule. So you assign lone pairs entirely to that atom where it's on. Shared electrons are divided equally between the sharing atoms. So there's covalent bonding, we share it equally. Atoms and molecules try to have formal charges as close to zero as possible. So you can't have a wild distribution of charges over your molecule. You want to have formal charges very low in charge, and this is the molecular formula that Lewis structure that you're trying to find. And then a very important part is, or issue is, that the negative formal charges must be with the most electronegative atoms. So if you have sulfur and oxygen, where would be the negative charge? Would be on the oxygen and not on the sulfur. That's important. And let's look at this. We look at NO2 minus. How many electrons is that? N is 5, and oxygen is 6. And we have 2 times 6 is 12. We have 2 oxygen, plus 5 is 17. And we have 1 minus. Is how many you have? So we have 18 electrons distributed with between 3 partners. How many resonance structures do you have? 2. That's how it looks like. So it's isoelectronic, you can say. That would be isoelectronic to ozone. If you have this, you know immediately what the dot structure looks like. So let's look at the nitrogen here. If we share the electrons equally, so you have, this is how it looks. There's the nitrogen, this is 2, 4, 6, 8. The oxygen has the octet. 2, 4, 6, 8. Oxygen has the octet. The nitrogen has 2, 4, 6, 8, also octet rule. So that's a very well balanced Lewis dot structure. If you look now at the nitrogen, so the free electron, let's go here, let's get to the rules here. The lone pair you assign entirely to the atom. So you give that to the atom, okay? So you have 2 right there. And then you do even sharing. You have 2, you share 1, so that's 3. And then you have 2, 4, 6, you have 4, you have 2, 3, and this is shared, so plus is 2. If you share this, these are 4, you share this evenly, then you have 2, so you add it up. This is 1, 2, 3, 4, 5, okay? So the shared electrons equally, this N is, the number is 5, and in the atom, in a regular free nitrogen atom, how many valence electrons do you have? 5. So, okay. No, I don't want to show this. This is what I want to show. This would be, the atom would be 5. So what would be the formal charge in this case? 0. Now let's look at this oxygen here, okay? So this oxygen, we share, has 2, 4, 6, 8. We share equally, okay? So that means it has 7, because there's one goes here and one goes there, so it has 7. And oxygen is in the free oxygen atom. How many valence electrons? 6. So you have 7 and 6. So 6 minus 7 is what? Minus 1. What's the overall charge? Is minus 1. But you can say, oh, professor, no, you're forgetting this one here. This is different than this one. I said, yeah, you are right. So what's it here? 2, 4, 6, 8. So we have 2, 4, 6. So what is it? It would be 6 on this one if you share it equally. And what is it in the free atom? 6. What's the number? 0. So the formal charge is 0. So I have 0 plus minus 1. So we were lucky that this was 0. That way I could brush it under the carpet. But you must clearly see that this has a different formal charge than this one. Okay? And so the formal charge, the sum of the formal charges, has to agree with your overall charge of your molecule, of your ion. If it doesn't agree, there's something wrong. Okay? So how does the formal charge of nitrogen change for the process? We have NO2 minus and we have NO3 minus. Okay, NO2 goes to NO3. So this has a formal charge, the nitrogen has a formal charge here, and the nitrogen has a formal charge here. And I'm asking you how it changes. If I go from here to here, does the formal charge increase, stay the same, or decrease? First, I would count the electrons. Draw the Lewis structure. Easy, okay? Draw the Lewis structure. I've shown you this before in some other cases. And then you give the answer. You need to determine what the formal charge is, and then you give the answer, and hopefully the right answer. So the first thing I would ask myself, you have seen this before. How many electrons is this? How many electrons is this? How many partners you have? You immediately have the resonance structures. Maybe I should show this to you. But now you need to determine the formal charge. So I'm going to give you the rules back. Ah, lots of people here. 250. Amazing, it's still that empty. Okay, that was to be expected. And I think you need to think about this. Does it increase the formal charge or decrease the formal charge? Okay, so how can I help you with this? Let me think about this. So you have, how many electrons does NO2 minus have? Valence electron. We always talk about the valence electrons. 18. That's an 18 electron system. Okay? All right. Now, how many does NO3 minus have? 24. That's like carbonate. It's a 24 electron system. All right. So now you can draw the structures and now figure out what the nitrogen, what the formal charge on the nitrogen is on NO2 and what is the formal charge on the nitrogen in NO3. Why don't you discuss this with each other? Come on, lively, wake up, wake up. Loud discussion, or you can talk about what movie you've seen yesterday or whatever. Okay? But have a discussion. That I get blood in your brain, or you get blood in your brain. From the stomach, where You know, Dr. Lee also has office hours where you can go and talk about the lab especially. On the nitrogen, not on the oxygen. Nitrogen, here. The formal charge on the nitrogen, not on the oxygen. I hope it doesn't change too much on the oxygen. Wrong direction. Okay. All right, so let's have a look at this. So, this was NO2 minus, and this is NO3 minus. What's the lone pair goes with the nitrogen in this case? Here we don't have a lone pair, okay? Then we have even shared. This is 1, 2, 3, 4, 5, okay? So what is the formal charge on this? 0, okay? What's the formal charge on this here? 2, 4, 6. Compared to 5 in the molecule, what's the formal charge? Okay, so this is plus 1. So the formal charge was here 5, and in the atom it's 5, so no change. And then it's plus 1 here, because it is now 4. 5 minus 4 is 1. That means plus 1. Did the formal charge on the nitrogen decrease or increase? Say again? Increased, okay. It increased. All right, you need to practice this. This will be part of the midterm, and I think there are things in the homework. So now comes the kicker here, a very difficult one. If you can answer this, you got it mastered. And there will be one of this degree of difficulty in the midterm. So I'm asking you now, about the bond order. So we have discussed what bond order is. So we have SO4 2 minus. How many electrons is this? So SO4 2 minus, you have to draw the resonance structures, possible resonance structures, and you have to follow all these rules here. Okay? And once you have done this, you can get the right answer. And the question is, what is the S sulfur oxygen bond order in the sulfate ion? So SO4 2 minus. That's the sulfate ion. Why don't you think about it and give me your answer? It's not easy. So that's the central atom. So you have 4 partners. There's several resonance structures. Very tricky resonance structures. And these are the rules we apply in our class. The book might have it a little different, but this is what I want you to do. I simplify it and make it much more logical. Sulfur and oxygen obviously have the same number of valence electrons, huh? They're the same group. Can you put the light on the periodic table, please? The light, please. Thank you. I know it's a distance to get to the switch. Thank you. But it illuminates now. There has to be, switch it off again. I think it has to be illuminated from outside somewhere. Not this one? Shall I? Yes. Thank you. They haven't fixed that yet. Okay. Did it count down? Or did I never start the display? Yes, it did count down, didn't it? Okay, so there's a pretty nice distribution here. So there are several possibilities to do that, but there's only one right one. Okay? So why don't you discuss this with each other? Yeah? Vivid discussion, please, because you got to get this right. You have to practice this at home and in the homework.
Because that has 6 bars.
Yeah, you're doing it all right, okay?
But how can it have 6 bonds around sulfur, though? Is sulfur just...
So, okay, maybe I tell you, sulfur can expand the octet. Everything in the third group, the third period, can expand the octet. Of course, we know now that the orbitals are a little different, but just from systematics, you could expand the octet in the third period. Sulfur is in the third period, okay? That may help you. Of course, you know now from orbital theory that the 4s is lower than the 3d, so you fill the 4s and then the 3d. But you have, essentially, if you go this way, you could expand this here, because you have the possibility for the d electrons. This theory was before orbital theory, the Lewis structure. So if some people must have gone home. Click in that you get bonus, okay? So there's 17 missing. No, 27, isn't it? Yeah, 27 were missing. Where are they? You never know what's happening. Okay, you said 1.5, and I agree with you. And so, but it's not this simple. So these are the structures. Let's start with the one on the left here. We have sulfur and oxygen. Sulfur has 6 and oxygen has 6. So 4 times 6 is 24 plus 6 is 30. So, and we have 2 minus. We have to distribute 32 electrons, okay? And you try not to violate the octet rule too often. And try to have the negative formal charges with the most electronegative atom, and have the charges as close to 0 as possible. So this one here is 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Very nicely, this is the octet rule is fulfilled. The sulfur is now plus 2, so this 2, 4, 6, 8. That would work, but I don't like it. Why don't I like it? Way too many charges on there, okay? Way too many. You have 4 negative and 2 positive. Is way too many charges. All right, I don't like it. Large number of distribution of charges, no good. Now let's look at this one. Now here we expanded the octet, obviously. We have 2, 4, 6, 8, 2, 4, 6, 8 octet, 2, 4, 6, 8 octet, 2, 4, 6, 8 octet, and then we have on the sulfur 2, 4, 6, 8, 10, 12, 14, 16. Okay? 16 electrons, so we have expanded the octet rule. We could do that, but there's something majorly wrong. Can somebody tell me what's wrong with that? The more electropositive has the negative charges. That means the negative formal charges must be with the most electronegative atom. So is oxygen or sulfur more electronegative? Oxygen is more electronegative. So negative charges on the less electronegative atom, out with it, okay? And so this what leaves us is this here. So we have 2, 4, 6, 8, octet rule for the oxygen, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So this is fine. And the sulfur we have expanded. The sulfur is 2, 4, 6, 8, 10, 12. And this you can do. And now we have a very small distribution of formal charges. You have -1 on the oxygen. It follows the more electronegative is -1. and -1 on this oxygen. So this is the most likely, that's the best structure. That's the one that you would have. So now, what was it? I asked what is the bond order, okay? So the bond order on what? On the SO, okay? So what was the bond order? Let me see. Just want to make sure that we have the right question. What is the SO bond order in the sulfate ion? So you have sulfate is 1 here, 1, 2, 3, 4, 5, 6 divided by 4 partners. You have 6 bonds divided by 4 partners. That must be 1.5, okay? The best Lewis structure, you have the octet rule exception, but you have 1.5 bond order, okay? Did you get that? It's simple once you know how to do it. Like everything else, it's simple, okay? and so you need to practice this. So that makes sense, this made sense, and so this makes the most sense, all right? So I just, for completeness, and we will use this later, you will also have heard about, or will hear about, oxidation number. Then oxidation number, we treat the electrons in the compound as if they were ionically distributed. As the more electronegative pulls all the electrons of the more electropositive. So you would have nitrogen, for example. You would have nitrogen, we divide up the electrons, and the more electronegative captures the electrons, okay? So this would be, this one, the oxygen would go, all the bonds would go here, and all the bonds would go to this oxygen. So you have, how many electrons you have left? 2, okay? So divide up the electrons. We really didn't divide up, we pulled them to the more electronegative. So N equals 2 compared to the atom. So oxygen would be 8, because they pull all the electrons over, so the nitrogen, they were taken away from the nitrogen, so we would have the oxygen 8. And now the oxidation number would be, compared to the atom, what would that be? 5 minus 2 is 3, and 6 minus 8 is what? So you have the oxidation number of +3 and -2. Okay, this is correct. Now, you always have to add it up. +3 plus -2 is what? Is -1. You have to do the same thing for formal charges. You have to add them up, and they have to give you the charge of the overall atom. All right? So just for completeness, because we need this when we do redox reactions, and I will bring it up then again. So today we're going to talk about more molecular binding in molecules, and we expand our knowledge. We're using the knowledge that we have together with a new model. So we combine the Lewis dot structure. We combine this with a new model, which is called the valence shell electron pair repulsion model, VSPER, and I will talk about this, but first I want to talk a little bit about this here. So if we look at this here, for example, this is C, has 2 carbons, 3 hydrogens, 2 hydrogens, so that's C2H5OH. Okay, this is a very popular substance. It's in many adult beverages, and it's called ethanol. It's alcohol, very much liked by the general population, sometimes too much, actually. And it has all kinds of consequences if you imbibe this, okay? So if we look at that carbon here, so you have 1, 2, 3, 4 partners. Just that carbon has 4 binding partners. Now let's take a simple carbon. This would be carbon, and I have 1 hydrogen here, 1 here, 1 here, 1 here. So this is CH4. What is that? CH4? Methane, okay? Now if I could have the camera on me, please. So that they can see me well, also my feet. All right. Should I stand up on the podium here? Okay. So, can everybody see it? So the carbon would be here. Okay, the carbon would be here. There would be one hydrogen. There would be another hydrogen up here, the hydrogens. Okay, these are the bonds. There would be one hydrogen by my right foot and one by my left foot. Would that be the most stable configuration? What would be more stable? To get these hydrogen as far as possible away from each other. This would be the configuration, okay? Not bad for a guy with a hip problem and back problems. All right, so you see that you're going to get a steric arrangement. And now I'm going to give you some rules under this valence shell electron pair repulsion theory will help you to go from the Lewis structure, dot structure, and then apply this VSBR to the dot structure, and then you can tell how this looks in 3 dimensions, how this looks in space, any compound. And so let's get started with this. And I put this on both screens that you can see it nicely. It will get there. There it is, okay? So, we start out with one partner, and you need to put me on camera again, and nicely big, that they can see all this stuff. So, my hand here is going to be the central atom, okay? I have a central atom. And it is bound to 1, 2, 3, 4, 5, 6 partners. 6 bonding partners. So we have 7, with my hand we have 7 atoms, okay? So if you look at this here, these 2 are in axial. They're standing in the rooms vertically. And these 4 are horizontally. So this is called an octahedron. You have octahedral coordination. And the bond angle between all these, the bond angle here, between this here, the vertical, and the horizontal is 90 degrees. And the bond angle is also 90 degrees everywhere, yeah? Okay? So this would be an octahedral configuration. With this, what would be our steric number? We define a steric number now. Steric number is the number of lone electron pairs. I don't have any lone electron pairs here, okay? Plus the number of bonded atoms. So this is my central atom. It has 1, 2, 3, 4, 5, 6 bonded atoms. Okay? What's the steric number? If you have a steric number of 6, the only way you can arrange the atoms around the central molecule is in an octahedral configuration. That's this configuration. Steric number 6 gives you an octahedral configuration as we have it shown here. Okay? Now, let's go to steric number 5. Please, go ahead. Please. Steric number 5. Okay? Oh, thank you. Steric number 5. So what do we have here? Let's see, they're a little bit too much blown up, so they don't do it quite. My hand is in this right hand here, is still the central atom, okay? And so you have 1, 2, 3, 4, 5 atoms bound to that central atom in the middle, okay? The only possibility to do this is a trigonal bipyramid. So this is one pyramid, and this is the second pyramid, and this is trigonal in the planar, in the plane, and this is, you still have 2 axial, okay? So what's the angle between those here? 90, and this is 90 between the vertical and the horizontal binding is 90 degrees. And what's the angle between these three here, each of them? It's 360 divided by 3 is 120 degrees, okay? So you have these 2 bond angles, steric number 5, trigonal bipyramid, and the steric number is 5, and the bond angle in the equatorial plane are 120 degrees, and the axial to equatorial is 90 degrees. So let's make steric number 4. Anybody? Steric number 4, let's use that white one. Oh, thank you. There, you can keep it, but no, you hurt yourself. That's not good. So, steric number 4. So let me see that here. So this is something like a, yeah, that looks like it. Actually, a little fold there. So you have steric number 4. What is that? A tetrahedron, okay? Has 4 equal sides. It's a tetrahedron. And there we know in a tetrahedron, the bond angle, so I need to push this a little bit more. Yeah, in a tetrahedron, the bond angle is, so they should move up a little bit more. You see the tetrahedron here on the screen. So you have one in the center, and then it points to the tops of the tetrahedron always here. One here, one here, one there, one there. So the angle between all of them, each of them, is 109.5 degrees. And if you have central atom and 1, 2, 3, 4 atoms that arrange around the central atom, the only possibility is you have it an arrangement, a tetrahedral arrangement, and this called the steric number 4. Now let's do steric number 3. Please. Steric number 3, keep it. Steric number 3, that's easy. That looks like it's a plane. See that? And this is trigonal, is a trigonal planar. It's a trigonal plane. And so we know now what the angles between those are here. Each of them is 120 degrees. So steric number 3 is trigonal planar, and the angle is 120 degrees. So now we have one more steric number 2. Steric number 2. Now keep it. Steric number 2. So this is linear. The angle is 180 degrees. Steric number 2, a linear arrangement. There's one molecule in the middle, and there are 2 on the side. They bind here to whatever it is. Now, steric number 1 is clear. We don't have to do that. But let's do steric number 1 and 0. Okay? And 0, just for the fun of it. Okay? Good, thank you. All righty. So you have now, if you can turn the light down a little bit more, please. You have now, was I up there on the screen? Yeah, good. You have now the valence shell electron pair repulsion model, the shapes. You have essentially 1, 2, 3, 4, 5 shapes. Steric number 2, 3, 4, 5, 6. Okay? These are the shapes that you have. And with this, there are some rules, and I'm going to give you the rule. We say you draw the Lewis structure for the molecule. That's what you do. That's what you know now very well. No big deal anymore. Use any of the resonance structures to predict the molecular structure, any of the resonance, which has to have a valid resonance structure. You know, resonance goes back and forth, so use any of them, okay? To predict the molecular structure, so you count each multiple bond as a single effective bond. So if you have double bonds, you count it as 1. Okay, in steric number. Count the electron pairs around the central atom, okay, the free electron pairs, and determine the position of atoms from the ways electrons are shared and arrange them so as to minimize repulsion. This is something we still need to talk about. Sounds very loaded, but it's not, okay? Name the molecular structure from the position of the atom. So it could be whatever it is, and you will learn how to do that. So let's go through this. Let's go through this. We have CO2, okay? Carbon and oxygen. What's the bond order? You rather have the rules or have the rules? So this is a single one. This is 1, 2, okay? You have any lone pairs? No. Good. So the bond order on that carbon is 2. With this, you have a linear structure, so there would be 1 oxygen here and 1 oxygen there. Okay? Would it have a dipole moment? No. Good. You can also have boron dichloride. Okay? Would be also linear. All right? So then we have the next one, trigonal planar. You have to have a steric number of 3 to fulfill trigonal planar. Boron trifluoride. Boron trifluoride, you have boron, which is how many electrons does boron have? 3. okay? And fluorine has how many? 7. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So this is fine. The fluorine have the octet rule fulfilled. The boron is 2, 4, 6. It doesn't have the octet rule fulfilled. It's deficient. We know that it's deficient. It misses electrons, and it's very reactive if it can catch electrons. Nevertheless, what is the steric number on this baby here? 3. And with this, steric number 3, it's a trigonal plane. All right? So it has boron sits here, there's a fluorine here, there's a fluorine here, there's a fluorine here. Okay? So with this, the angle is 120 degrees between these here, okay? Between the boron and the fluorine. So then we have NO3 minus. NO3 minus. What's the steric number there? It's 3, yeah? So how many electrons is that, the NO3 minus? NO3 minus, how many, what's an electron? Huh? 23. Minus? 24. NO3 minus is the 24 electron system. How many resonance structures you have? 3. Excellent, okay? Good. So, and since we count single and double bonds as the same, we have no trouble. We said 1, 2, 3, steric number, no free electrons, isn't there? Okay, good, because there's a double bond there. So this would be, the nitrogen would sit here, and the oxygen would sit here, here, and here. Good. Steric number 3. So multiple bonds, we know that there's one double bond in there, counts as one effective electron pair. So now let's look at C2H4. So there's a double bond. Now let's look at this one here, the carbon. What's the steric number on the carbon? 3. That would be that carbon would sit here. There would be one hydrogen here, and what would be here? It would bind to that carbon. There would be another lobe coming from the carbon, which would bind here, and then you would have the other carbon here, and the hydrogen would be here and here. So you just take a mirror of this, and you get the mirror symmetry here. So this is the trigonal planar, because the steric number is 3. Now let's look at tetrahedral, a tetrahedron. So that's steric number 4. And we look at methane, CH4. That's what I've showed you, CH4. And it was already like this, okay? So it was 1, 2, 3, 4. This is the steric number. So there's the carbon here. And here is a hydrogen, here's a hydrogen, here's a hydrogen, here's a hydrogen. So the bond angle, because it's a real tetrahedron, is 109.5 degrees. All right? So now comes something special. If you look at water, let's see what's the steric number on water. So you have 1, 2. Each pair you count as 1, so you have 2 pairs. That's 2. Plus the bonded ones, 3 and 4. The steric number of water is what? 4. And with this, water forms a tetrahedron. So this is strange, isn't it right? So you would have the oxygen here, then you would have a hydrogen here and a hydrogen here, and there you would have a free electron zipping around, pair zipping around, and a free electron pair zipping around there. Okay? But now you have negative charges here, negative charges here, and so you have a repulsion. That means it squishes that angle, that bond angle, and you have 2 free electron pairs. They squish that bond angle dramatically from 109.5 to 104.5 degrees. So there's a difference of 5 degrees here in that the angle got smaller because of these 2 free pairs. They were squishing on it, okay? Let's have another example. That's a sort of a V-shaped arrangement, but it's tetrahedral, but if you look at it, it's a V-shaped, okay? But because you can't see these free electron pairs. So that's called the lone electron pair compression, where the lone electron pairs compress the angle between the bonding pair. Now let's look at another compound. NH3 is ammonia. So the nitrogen has 5 free electrons, okay, in by itself. So it has it's bound to 3 hydrogens, 1, 2, 3, and 1 lone pair. So the steric number is 1, 2, 3, 4. Steric number 4 gives you again tetrahedral configuration, but you have the darn lone pair, which pushes on the other electrons and pushes them together a little bit. Not as hard as here, because you had 2 lone pairs, but harder than here because there's no lone pair. So that bond angle is 107 degrees in the ammonia, this bond angle, okay? So that's 107 degrees, and with this you have learned about the lone pair compression effect, or the lone pair effect. And I'm going to show this one more time to you, the electron group repulsion. So CH4, you have no lone pairs. Then you have NH3, you have 1 lone pair here. Here would be that lone pair. It compresses this here to get that angle to 107 degrees. And here oxygen, you have 1 lone pair here, 1 lone pair here. It looks like a V, but it's not, because you have these lone pairs. And the angle is compressed to 104.5 degrees compared to 109.5 if there's no lone pair compression. Okay? So we come now to steric number 5. So you have a central atom, which is bound to 1, 2, 3, 4, 5 other atoms. Phosphorus pentachloride, penta means 5, would be such an example. So the chlorine has 2, 4, 6, 8, so the chlorine is fulfilled, the octet rule. How about the phosphor? 2, 4, 6, 8, 10. So phosphor is, see, it's in the 3rd period, so you can expand that octet, all right? If you, anything below the 2nd period, you can expand that octet. That means you have 2, 4, 6, 8, 10, 2 electrons too many. You have a 2 electron expansion, but you have 1, 2, 3, 4, 5 electron pairs. With this, the steric number is what? 5. And you have that trigonal bipyramidal arrangement. So 120 degrees in the plane here. This is 120, it says right there, and 90 degrees between the plane and the axial bonds. That would be one possibility, and now we come to a tricky thing. If you look at iodine trifluoride, iodine and trifluoride, they are both in the 2nd to last group. So how many valence electrons each of them have? 7. So we have 1, 2, 3, 4 times 7 is 28, and then we have 4 times 7 is 28. Okay, so we have 2, 4, 6, 8. 2, 4, 6, 8. This is okay. 2, 4, 6, 8. This is 3 times 8 is 24. 26, 28. We have 2 free electron pairs. 2 free electron pairs. And now you would think, my God, it can't be like this. Why would that be not a T-shaped? It is actually T-shaped. Why would it be a trigonal bipyramidal? Because you have these 2 electron pairs here in this plane. Okay, this is in the axial, and these are in the plane. And with this, it's not totally linear. They compress this a little bit, and it would be maybe something like this here, a slight angle here in between. It's not, but you can call it T-shaped, essentially. This is one of the kickers in doing this VS-EPR method, okay? So let's go to the last one. And now let's use xenon tetrafluoride. You know, I talked to you that xenon can react at very high and very strong chemical conditions, high temperature, high pressure. And so xenon has 8, 2, 4, 6, 8, 10, 12. So we exceed the octet rule for xenon, we can do that. And for fluorine, we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So that means, what's our bond, what's our steric number? It's 1, 2, 3, 4, 5, 6, okay? Steric number 6, it must be octahedral, and this is how the octahedron looks like. And in this case, for example, would that be magnetic? Xenon tetrafluoride? No, exactly, okay? And sulfur hexafluoride, so you have 6 fluorine. What's the steric number for that? 6, exactly. Sulfur would be here, and you would have the 4 fluorides here, right? So this is, for example, xenon tetrafluoride. You had heat. It was xenon was heated with fluorine, a very reactive compound, at 300 degrees and 6 atmospheres of pressure in this gas, and you get these colorless crystals of xenon tetrafluoride that sublime at 115.7 degrees. And with this, I'm not going to ask you this question. I'm going to start the next lecture with this question if we pick up where we have left off now. And I see you on Wednesday.